Hello, it's me, Maria Sandoval, and today I will be presenting on effusion and a few other gas equations. So, Graham's law of effusion. Effusion is the process by which a gas escapes through a small hole in its container into an evacuated space. Like you can see here, effusion, the lighter black particles effuse faster than the red, heavier particles because they're lighter. That means that they can fill the space faster. Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass, right here. A lighter gas moves more quickly and therefore has a higher rate of effusion than a heavier gas at the same temperature. The rate of effusion is 1 divided by the square root of the molar mass. Here we are applying Graham's law of effusion. So here's a mixture of helium and methane, and we're hypothetically saying that it's placed into an effusion apparatus to calculate the ratio of their effusion rates. The effusion rate is proportional to the square root of the molar mass for each gas. So for our plan, first we need to find the molar mass for each substance using its formula and take the square root. The ratio of the effusion rates is the inverse of the ratio of the square roots. So for our solution, first we need our molar masses. So here's the molar mass of methane, which is 16.04 grams over moles. And then we have our molar mass of helium, which is 4.003 grams over moles. So we have our rate of helium over our rate of methane, which is this, we're going to put it in the square root, 16.04 over 4.003, which gives us 2.003, which means that our helium, if you look at it, is much faster than our methane. I'm waiting for the slide to react. Okay, so moving on, these are van der Waals constants for some common gases. So here are our gases, and here's A, which is the atmosphere times liters squared over moles squared, and B, which is liters over moles. So for helium, you can see it goes across. I don't want to read out every one of these numbers, but I'll read out like the most common ones that you'll find, like H2O. Here for A it has 5.46, but it doesn't have anything for the B. And then NH3, which is your ammonia, it's 4.17, and then 0.0305. CO2, your carbon dioxide, 3.59, 0.0371. The chlorine, it's 1.36 to 0.0562. You have your argon, which is 0.211, and then 0.0322. Your helium, which is 111.122, and 0.0237. You get the gist of it for the main part, but this is how they found those numbers, by putting in these equations. Moving on to another sample problem. Here's a sample problem for solving an unknown gas variable at fixed conditions. So let's say that there is a steel tank that has a volume of 438 liters and is filled with 885 kilograms of oxygen gas. Calculate the pressure of oxygen gas at 21 degrees Celsius. We are giving our volume, temperature, and mass, which can be converted to moles, which we're going to write as N. Use the ideal gas law to find the pressure. So for our solution, we are given the volume, which is 438 liters. We are given the moles, which is 0.885 kilograms of oxygen. We need to convert it to moles. And we're given our temperature, which is 21 21 degrees Celsius, but we need to convert that to Kelvin, and it's already done for us here, and it's 294 Kelvin. Our pressure is unknown, and that's what we need to find out. So here we have our 0.885 kilograms of oxygen times 10 to the third grams, because we're converting our kilograms to grams so that we can convert our grams to moles, which gives us our 27.7 moles of oxygen gas. Here we are using the formula P equals nRT over V to find out our pressure, because we need the pressure and we get it at the end. So 207, we're putting our moles of oxygen here. We're timesing it by 0.0821. Atmospheres times liters, moles times Kelvin, times 294.15 Kelvin. Our Kelvins cancel out, our moles cancel out, and our liters cancel out because we're dividing the whole thing over 438 liters, leaving us with 1.53 as our atmosphere. And that's solving for an unknown gas variable at fixed conditions. So, I think that is all for today, but I just want to double check that I did not miss a slide, because as you can see, my computer is being a little slow, so I can't tell. I'm not sure. I don't think we got to go over this, and that was one of the slides. So I'm going to go back to this and talk about it, because yes, I think I remember it skipping over it. I'm sorry about that. So for real gases, the deviations from ideal behavior, we are going to talk about how the kinetic molecular model describes the behavior of ideal gases, and real gases deviate from this behavior. They have volume, and gas particles are not points of mass, but have volumes determined by the size of their atoms and the bonds between them. Real gases do experience attractive and repulsive forces between their particles, and real gases deviate most from the ideal behavior at a low and high temperature. And then what we did on the previous slide, since I skipped past this, was the van der Waals equation, which adjusts the ideal gas law to take into account the real volume of the gas particles and the effect of the interparticle attractions. Van der Waals equation for n moles of real gas. And in this, the constant A relates to the factors that influence the attraction between the particles, and the constant B relates to the particle volume. I'm sorry that was a little out of order. My computer's been giving me some technical difficulties. But I hope you have a great night, and I hope you learned a little bit, because I learned a little bit more in every one of these. Thank you. Bye.